Hello, everyone, and welcome to CW Trending. My name is Jeff Sloan. I'm Editor-in-Chief of Composites World. CW Trending is a new product for CW. This is a video-based program designed to explore the people, ideas, and, as the name implies, the trends that are shaping the composites industry. And our topic in this episode is composites use in infrastructure, or in deference to one of our guests, Gareth Williams, since he's from the UK, it's composites use in infrastructure. So what we have two presenters today. They're Joe Fox and Gareth Williams. We're going to hear from each of them first. I'll ask them a few questions when they're done, and then we're going to open it up to Q&A from you, our audience. So if anybody in the audience has a question at any point during the presentations, you can type that question under the question tab in the webinar dashboard. The chat function is also available if you want to chat with other attendees. If you do post a question in the chat, we'll try to grab that and move it over into the Q&A tab so we can pay attention to that. We'll try to get through all the questions, as many as we can, before we wrap up here. And so I want to thank you for attending. So let's go ahead and get started. Our first presenter today is Joe Fox. Joe is president of FX Consulting, a consulting firm for the specialty chemicals and materials industry. Joe is a chemist by training and has a bachelor's degree in chemistry from Lehigh University and a PhD in chemistry from Penn State. He worked also for several years at Ashland and then eventually what is now INEOS. Our second presenter today is Gareth Williams. He's an aeronautical engineer who developed world-leading research into self-healing carbon fiber composites during his PhD at the University of Bristol. He is currently the strategy director at the National Composites Center in Bristol in the UK. So Joe, I'm going to turn it over to you and let's get started.
All right, very good. Well, thank you, Jeff. It's a pleasure to be here. And as my title suggests, in the next 10 or 15 minutes, I'm going to connect FRP Composites to two important documents from the American Society of Civil Engineers, or ASCE. Those documents are their 2021 Infrastructure Report Card and their Future World Vision. And I'm really going to try and emphasize the trends that are in those two documents. So I'm going to start with my take-home message and finish with my take-home message. And my take-home message is that there is an extremely good fit between FRP Composites and our nation's infrastructure needs, both today and in the future. I strongly believe that to be the case, and I hope you will too when I'm done with my presentation. So this slide lists some of the key attributes of FRP Composites for infrastructure applications. They are lightweight, easy to install, corrosion resistant, extremely durable, and resilient. Now, all of these are important for infrastructure and construction applications, but as a member of ASCE, I know that resiliency right now is a particularly hot topic. So a little bit about the 2021 Infrastructure Report Card. This is a document that ASCE releases every 4 years. They put a lot of effort into this report card, and it gets a lot of visibility and a lot of attention on Capitol Hill. The 2021 version was released in early March, and you can see the scores here. And needless to say, this is not the kind of report card that you want your kids to come home with. There are only 2 B grades, there are 4 C grades, and the rest of the grades are either D, D minus, or D plus. The overall grade improved slightly from a D plus to a C minus in 2021, but still very disappointing. Now, ASCE divides infrastructure into the 17 categories that you see here. I'm not going to have time to talk about all of them. I'm going to talk about 7 of them. So there are many opportunities for improvement, and let's start with bridges. They get a C. FRP has been used to construct more than 500 bridges in North America. The most notable examples come from the states of Florida and Maine. I'm going to highlight the state of Michigan on the next slide, and there's also been considerable bridge activity in Canada. As you can see from the pictures, there are long span bridges, there are short span bridges, there are bridges over rivers, there are bridges over highways. Some of these bridges use elements that are made completely out of FRP rebar. Others use FRP rebar to reinforce concrete, or both. FRP has also been used to strengthen and repair bridges. In this case, FRP wraps, like the one shown here, are used to strengthen and repair the bridge. This is usually done with carbon fiber reinforced polymer wraps because CFRP is stiffer than glass fiber. Originally, this technology was used in California to provide resiliency against earthquakes. Remember, the resiliency is important, but it is used in other places. And here, for example, is a picture of the Rouge River Bridge, which is Michigan's largest bridge, and MDOT has used these CFRP wraps to strengthen more than 200 columns on that bridge. There are many other examples of FRP strengthening, and sometimes this type of repair is referred to as bonded FRP or externally bonded FRP. And actually, AASHTO, the American Association of State Highway and Transportation Officials, has issued this manual on the use of bonded FRP systems for repair. FRP can also be used for pedestrian bridges and walkways. And the key attributes here are lightweight and durability. And here are some examples from Ohio and from Lake Tahoe. FRP can also be used to add pedestrian walkways to an existing bridge. Here is an example of a cantilever walkway that has been added to an existing bridge in Niagara, New York. So what you've got here, FRP was selected because it enables you to add the walkway to the bridge without adding a lot of extra weight. And what you've got here is lightweight addition to an existing structure. And I want you to hold that thought, that trend, that concept, because I'm going to come back to it a little bit later when I talk about future world vision. Let's move on to water infrastructure. I think we're all familiar with the impact of aging infrastructure on our water supply. The ASCE report card says that nearly 6 billion gallons of treated drinking water are lost per day due to leaky pipes. 6 billion gallons, that's nearly 15% of the US drinking water supply. And I think we're all familiar with what happened in Flint, Michigan. Water from the Flint River was used instead of water from the Detroit water system. The water from the Flint River was more corrosive, and it leached lead from the pipes into the drinking water. When you go to Capitol Hill and talk to the legislators there, believe me, no one wants to have a Flint, Michigan happen in their state or their congressional district. And then there are water main bursts due to old pipes. The report card says that there are more than 250,000 per year. When they occur, they can lead to significant damage, and when they occur in major metropolitan cities, they can lead to major disruption. So let's talk about some opportunities for improvement with FRP related to water. We'll start with drinking water and wastewater. They get a C- and a D+ respectively. So FRP has been used for pipes for drinking water. The important attributes here are corrosion resistant and durability. FRP pipes do not contain any lead. And to be used with potable water, they need to pass a test called NSF 61. FRP can also be used to repair leaky pipes. There is a technology known as cured in place pipe, or CIPP. It is a trenchless repair technology where basically you insert a sock into the ground, fill it with resin, allow the resin to cure, and you form an impervious shell inside the existing pipe. This can also be done by taking preformed liners underneath the ground. FRP can also be used for wastewater infrastructure. This is a cartoon of a typical wastewater plant, and there are many different places where FRP can be used in this plant. It can be used in the pipes. It can be used in the covers and the scrubbers and the ductwork and the baffles near the settling ponds. It can be used in the storage tanks used to hold the aggressive chemicals used to treat the water, things like bleach, hydrochloric acid, and sodium hydroxide. And it can be used in the stairways, the gratings, the handrails, and the walkways throughout the facility. In all of these applications, you're taking advantage of the excellent corrosion resistance of FRP. Let's stay on the water theme and talk about dams, inland waterways, and levees. They all get D grades in the report card. And here are some pictures that show how FRP can be used in inland waterways. It's used in locks, in wicket gates, is used to protect bridges, and these FRP piles are used to support these navigation aids. In all of these applications, you're taking advantage of the excellent resistance of FRP to water. And we'll finish up with ports. They get a B- in the report card. FRP has been used in all kinds of waterfront and coastal applications. FRP piles have been used in these piers, in this seawall, in these dolphins at this ferry landing. And here is another example of a fender, in this case, protecting a pier from impact damage. So, to come back to my take-home message, I hope I've shown you very quickly that there is an extremely good fit between FRP Composites and our nation's infrastructure needs right now. I didn't have time to talk about all 17 categories. I talked about 7. 2 of those categories had C grades. 4 of those categories had D grades. So there is definitely room for improvement. And FRP can help get these grades up right now. So next, let's talk about the future. Now I want to connect FRP Composites to the other document from ASCE, and that is their future world vision. And that is exactly what it says. It is ASCE's vision of what cities of the future will look like. And you can get a lot of information and some very useful videos at this website here. Now we're in a session called CW Trending. And Future World Vision is all about megatrends and how they are going to impact cities of the future. So there are 5 different scenarios. I'm going to talk briefly about 2 of them. The first is floating cities, which ASCE predicts that we might begin to see the first floating cities around 2040. A little bit of history here. In October of 2019, I attended the ASCE annual meeting in Miami. I attended as a non-member, but I quickly decided to join ASCE. What convinced me to join was the Floating Cities virtual reality exhibit. Floating Cities is a part of Future World Vision. And here are 2 pictures from the conference. This is not me, but this is one of the attendees with the virtual reality goggles on. What you did was put the goggles on and go out to a floating city. And you could look all around and see the infrastructure above the city, the buildings above the city or above the water, and then you could look below the water and see the substructure of the city. This was by far the best virtual reality experience I have ever had. And if you ever have a chance to experience this, you should. It is truly amazing, extremely well done. And it got me really excited because I saw a very good fit between FRP and this vision of the future. So a little bit about FRP and trying to show you the tie between FRP and floating cities. So I'm going to do that showing some pictures from ASCE videos and articles and also some real world examples. First of all, you're talking about a floating city here. So the most important thing is that it needs to be able to float. And so FRP is a perfect fit because you want everything above the surface of the water to be lightweight, the buildings and the bridges. FRP is 1/5 the weight of steel. It is 30% lighter than concrete. So if you want this thing to float, you want lightweight elements. And that is what FRP provides. If you look below the surface of the water, remember we're talking about coastal cities here, like Miami and Singapore. They're going to be in corrosion or corrosive seawater. What you're going to want is corrosion-resistant construction below the water. And that is another place where FRP excels, corrosion resistance. And then you're going to want resilient structures around the city, structures like seawalls and structures that can prevent damage from hurricanes and storm surge and sea level rise. And I've already shown you how FRP is used in things like seawalls and piers. So if you look at these pictures and you see what FRP is capable of, there's a very good fit between FRP and floating cities. Now, some of you might say, yeah, but when are we going to see floating cities? And I said ASC predicts that it'll be out in 2040. But there are other scenarios. And I want to talk about the other scenario, which is megacities and smart cities, which is much more immediate and much closer to the present. So again, I'm going to be using pictures from ASCE articles and real-world examples to show the fit here. Remember, I talked about the lightweight addition of a pedestrian walkway to an existing bridge. Lightweight addition to an existing structure. That's going to be a very important trend when it comes to megacities, because here's a picture where you're seeing some unmanned or manned vehicles, urban air mobility in megacities, and you're going to need places for those vehicles to land. And FRP would be an excellent choice for the addition of lightweight heliports to existing buildings. It may also be possible to add additional living and working space to existing buildings by adding these lightweight composite modules to the exterior of an existing building. Future World Vision also talks about drone delivery and prefabricated structures. And here's a picture that came from an ASCE article, which shows a drone delivering a girder to a job site. And when I saw that picture, I instantly thought of an FRP girder that has been developed and tested at the University of Maine and commercialized by an industrial partner. And that FRP girder is 70% lighter than a steel girder, which would make it much easier for this drone to deliver it to the job site. ASC also predicts greater use of prefabricated structures. And here's something that's already happening with FRP. This is a composite foundation for a residential home. And it is assembled by bringing these prefabricated panels to the job site and assembling the basement in a fraction of the time that it takes to make a traditional poured concrete basement. And then lastly, FRP could have a very good fit in smart cities, where 5G will be important for communication. For 5G communication, you're going in megacities, you're going to need many more antennas, and you're going to need materials that are transparent to RF radiation, high frequency, short wavelength radiation. And FRP composites are transparent to RF radiation. So they may be able to find widespread use in a megacity and enable better communication between buildings and within a building. And as an illustration of that, this is an FRP light pole that is already in place in Europe. And it does not only serve as a light pole, it also serves as an antenna because it is RF transparent. And this one here even has a charging station for small drones at the top. So lightweight, prefabricated, easy to install, RF transparent. Again, there appears to be a very good fit between FRP and this vision of megacities and smart cities of the future. And really, when you think about it, that future is right now. So I'm going to finish up where I started, that there is an extremely good fit between FRP composites and our nation's infrastructure needs, both today and in the future. You can use FRP to convert those C's and D's into A's and B's today, and I've shown you how it fits with scenarios like megacities and floating cities of the future. Many of the trends that I've talked about in my presentation bode very well for the future of FRP. And that concludes my presentation, and I look forward to the Q&A.
Excellent. Well, thanks everyone for attending today, and it's a privilege to be able to present to everyone. So Joe has given an excellent presentation and overview on the kind of huge range of opportunities for composites in infrastructure and construction. So my focus, at the National Composites Centre, we have a broad view, and our responsibility is to drive the use of composites into all sectors, all industrial sectors, and driving the latest technology, the design and manufacturing technologies to introduce and support those. So we have a really good view of the challenges across multiple sectors. So what I'm going to focus on here is if the case is so compelling for composites in construction and infrastructure, what's actually stopping the adoption of that technology and its widespread use? So again, more generally, why composites in construction? Why do we actually want to look at that? So there's kind of 4 primary drivers at the top that we focus on. So one is around longer life and low maintenance infrastructure. And Joe pointed to a number of those applications, particularly where you're exposed to more corrosive environments, and where you actually want to have infrastructure that you have more potentially and conceivably more predictability around its degradation mechanisms, and that actually you've got a longer usable life out of that asset. The other ones are more efficient homes and buildings with potentially a reduced carbon impact. So some of the thermal properties of composites can be really advantageous in the use of home buildings, and can be really favorable from an embodied energy perspective. The other is low impact construction methods and materials. So generally the installation footprint of composite structures and some of the alternate methods that you can use to maybe as far reaching as the drones that Joe pointed to can become an option for composites, whereas with the kind of incumbent technologies in the sector, that's not necessarily possible. And the other is kind of a self-reinforcing opportunity here for modular off-site construction. And so that's another way of actually productionizing the use of composites in construction, which helps drive down the cost, which, as you'll see later, I'll reinforce is that this can be a challenge with the adoption of composites. But then just, I guess, more generically, there's the opportunity for reduced installation. So actually completing some of the kind of one part lifts the installation time, and the reduced disruption to operations around a construction facility, particularly when you look at roadway infrastructure and things like that, installing bridges. The disruption to that infrastructure can be minimized because it can be a much reduced installation footprint. The ability to combine form and function, and that really goes hand in hand with the opportunity for architectural impacts. So you're not necessarily looking at a structural component and then have your interesting features reinforced with cladding and other, I guess, non-structural materials. With composites, you can actually combine both because of the manufacturing properties, which is really interesting to see some of the visions that architects have actually being able to come to reality when you select composites as a material of choice. And also that reinforcement that composites are not just for niche applications in small kind of minimal load bearing applications. They're used, and there's examples worldwide of where composites have been used for performance at scale. So what's stopping us use it? As I say, the value proposition is so compelling with composites, but why are they not just adopted? And many of you will recognize some of these challenges. So the first 4 I've identified is around knowledge. So there's potentially limited knowledge within the sector. Those engineers that are civil engineers, gone through civil engineering training, and having that limited access to knowledge to be able to identify composites as a viable opportunity. And also that the tenders, the procurement processes in the sector can sometimes be prohibitive. Not necessarily intentionally, but people writing the tenders might not have the knowledge base to be able to open up maybe a performance criteria where composites could be an option for the solution. Standards, there may not be the relevant standards that people can design to for different applications of composites. Skills and workforce, widespread skills and training, not necessarily prevalent. It doesn't necessarily feature heavily in the curriculum for civil engineering and some of the associated skills for construction infrastructure and the supply chains. As an aggregation of all of that, the supply chains are not generally equipped to support the introduction of these innovative technologies, and also the incentives aren't necessarily there for those supply chains to innovate in response to the available tenders. The other 4, cost. So typically, and this is a kind of a self-defeating issue, the low uptake of composites generally makes the introduction of a composite product less competitive from a cost perspective. But as you'd see more uptake of composites use, you can start to commoditize the production, and particularly manufacturing techniques such as protrusion come into play in construction, and can be a good way of commoditizing that production. And the introduction of those materials like RHS sections in composites, for example. Sustainability. So I guess historically composites do have an end of life challenge. That's more of an acceptable challenge if you're, for example, doubling the operational life of an asset. But there's an opportunity there to start to develop circular economy approaches, and with the NCC, we're pushing right at the forefront of sustainability issues and try to address that challenge so that it doesn't become a barrier, continue to be a barrier to entry in multiple markets for the use of composites. The market, how the construction and infrastructure market is created, so the benefits owners really align with the risk owners. So in terms of the supply chain development, introduction of new and innovative technology, if the risk sits somewhere and the benefits of using that new technology sit somewhere else, then you've got to break down in the system there. So we need to make sure that the benefits and the risk owners are incentivized in the right way to encourage innovation and alternative solutions. And data. So people may have the knowledge, they may have access to the standards, but if they don't have the relevant data, for example, fire and toxicity performance in accordance with the standards and codes relevant for that sector, then there will still be a reluctance or an inability to access those materials. Otherwise, you will need to go back to square one and produce those data sets on a case-by-case basis, which can be time and costly. So I'm going to draw up 3 focus points to conclude the presentation. The first one is around sustainability, and as I said, the National Composite Centre, we're working with our membership base across multiple sectors to really take what's historically a linear life cycle for composites and make it more circular. So at the end of life, we have more options to either repair, reuse, recycle, or return that material back to raw. So recover in particular the really useful parts, the high value parts, which is the fibre, and also do something very useful with the polymer chemistry that forms the matrix. But what we see is the potential for a really interesting waterfall cascade, where you typically take a high performance, low volume material, you recycle it, and generally you degrade the performance of that material, that fibre, somewhat in the recycling process. But the opportunity to then re-enter another stage in another industry, another part of the value chain as a really useful product. So you create that supply and demand, and ultimately ending up in what you would typically recognize compared to some of the high performance aerospace structures, a low performance, high volume application. And then you've got a really good model there to a circular model for continued reuse of those composite materials. The other one is the market. I think this is really important, and you see this across multiple sectors, where the value proposition for changing into a new material, companies might like the principle and the benefits that Joe's outlined, and there's great examples of where they've been used. But if the supply chain is not really constructed in the right way, whether the standards are actually, the tenders, the procurement processes don't incentivize or land the right risks and benefits with the right owners, then it's self-defeating. So there's no incentive to change, and the benefits that we've talked about in terms of composites, the asset owners are very interested in those, but I guess the installation part of the supply chain maybe carries the risk of taking on that new technology. And so we have to make sure that the supply chain, if we want to encourage that change, that we look at new ways to incentivize the right behavior and incentivize innovation, and looking at the way in particular that doesn't become restricted or prohibited by closed specifications and tenders, where metal solutions or the incumbent material is the only viable solution because it's closed down by the tendering process. And lastly, the industry is not dealing with these challenges in isolation. One of the things that we see, because we serve every sector, and we're introducing composites in growth sectors where they're not used to using composite technology, like construction and infrastructure, like energy. We actually work across the board, and we can recognize the challenges that multiple sectors face. And so a collaborative approach to addressing some of those challenges can reduce the burden, and other industries that are maybe not as mature in their adoption of those technologies can learn from other information and knowledge that's generated in parallel sectors. So that's what we try and foster. But at the top level, there's a challenge of creating zero carbon, generating zero waste, and creating zero harm in our projects. And across multiple sectors, so mobility, energy, construction, infrastructure, medical, healthcare, food and agriculture, some of the recognized industrial sectors. And then if we look at the barriers to entry that I've outlined, the only one that doesn't, obviously, isn't a carbon copy potentially across those sectors is the market construct. And that's very different depending on each market, but some of the similar challenges. How do you construct a market to incentivize the behaviors, the adoption of new technology that you want to stimulate? But when you look at the knowledge, standards, skills and workforce, supply chain, cost, sustainability data, there's aggregated demand for those. And so a cross-sectorial approach to some of these, or knowledge sharing between key sectors that have overcome some of these challenges and have used composites, widespread adoption, and have overcome that challenge of addressing those barriers to entry. We're well positioned, collectively as a composites community to help to bridge that. So no sector really is what I'd say an island in solving these challenges. And there's always someone that has maybe not addressed the same challenge, but we can cross-pollinate technology, we can cross-pollinate knowledge and learning. And that's really what we should be doing to help accelerate TRL scales for technology in new sectors. And that's the end of my presentation. Thank you very much for listening to me.
All right, great. Thanks, Gareth. And we'll bring Joe back in. I appreciate both of you for those presentations. So before we get to attendee questions, which we have a few of already, I have a question, two questions for each of you. So I'm going to ask you first, Joe, and Gareth, I'd like to answer the same question. And attendees, if you have questions, go ahead and start putting them in as well. We'll get to those here in a second. My first question is, Joe, Gareth referenced the fact that the first cost for composites are relatively high. There's also a sustainability story to tell, and that maybe offsets the cost. I'm wondering what each of you sees happening in the infrastructure community right now. Is that first cost argument still holding, meaning is that still the primary concern, or is the sustainability argument starting to win over and prove the viability of composites use?
So I'll try to answer this first. With respect to first costs, I think it's fair to say that in most instances, using FRP, for example, in place of steel or concrete, you are going to have a higher first cost. But I've been given a webinar to various ASCE chapters, and one of the things that I highlight is a life cycle cost analysis for the Halls River Bridge in Florida. It's been conducted by the Florida Department of Transportation and the University of Miami. And they clearly show that if you factor in the life cycle costs, where you factor in the lower maintenance costs, the lower repair costs, the lower replacement costs of FRP, that over the life cycle, FRP is a winner. Okay. There are also some examples, particularly from advanced infrastructure technologies, which has been very active in putting bridges throughout New England, mostly in the state of Maine, that they have shown that the first cost of installing some of these bridges with FRP is lower than the traditional concrete solutions. And so when you look at life cycle cost, I'm also involved with ICMA's efforts to get legislation on Capitol Hill that spur the use of composites. And a lot of that legislation is really asking the state departments of transportation to focus not just on first costs, but on life cycle costs, because ultimately you're going to spend more money if you have to do a lot of maintenance, repair, and replacement. Okay.
Gareth, what are you seeing?
Yeah, I'd reinforce that. I think generally when you have a compelling challenge or driver where composites have a really compelling case, like you've got an extremely corrosive environment, or it's restricted in terms of your lifting capacity or something like that, then first costs can be overcome by, it becomes a lot more compelling when you have that ultimate driver where some of the benefits of composites override the cost. But I'd reinforce, what Joe said. Were the words that we get people to look at is the whole life cost. So yes, sometimes the upfront cost until it gets commoditized or there's widespread adoption of composites in construction and infrastructure. You need to look at the whole life cost, and that's not unique to construction infrastructure. It's the same with energy, and other industries have already overcome that challenge and do consider the whole life cost. But that's where I come back to the market construct in construction infrastructure, because if the organization making the decision on the procurement exercise doesn't care about the whole life cost, because they won't have the asset, they won't maintain the asset, they won't solve the downstream problems, then they still won't be incentivized, even from a whole life cost perspective, because their part of the share is the upfront cost and carrying that risk. So I think that needs to be overcome. But one of the other things on the other side is the opportunity to do the right thing. And what we're hearing from a number of companies that we're working in construction and infrastructure is the real interest in using recycled materials from composites. So, for example, we've got a key initiative called SUSWIND that we've launched, which is working with the wind industry to solve the challenge around recycling for wind turbine blades. And what we're doing in that program, really interesting, is trying to create that supply and demand side of the market, so that we have companies in construction and infrastructure that are really motivated to use recycled materials because they want to do the right thing and they want to provide an outlet for those solutions, with the suppliers, if you like, that have a problem in their recycling challenge. So if you can connect the two, you create a good market for recycler, and it also opens up a good additional use for composites in construction and infrastructure because of the reduced CO2 footprint and the good story that comes with using recycled materials that would otherwise potentially not have an application.
Jeff, I wanted to just add a little bit more about sustainability. I focus mostly on life cycle costs, and they're not completely disconnected. But in terms of sustainability, when you use FRP in place of traditional materials of construction, there can be energy savings and transportation savings. So you've got lightweight materials. So it costs less to get the materials to the job site. Right. You need less equipment at the job site in terms of cranes and heavy equipment. All that translates into labor savings and energy savings. When it comes to emissions, one of the biggest creators of carbon dioxide is the production of cement. So whenever you replace concrete with FRP, you are lowering emissions. Whenever you use FRP rebar to replace steel rebar, to replace concrete and make it last longer, you are lowering emissions. So FRP has a very good sustainability story to tell. Okay.
All right, so next question, I'll start with you, Gareth. Joe just mentioned rebar. And recently in Miami, we had a collapse, a tragic collapse of an apartment building. And I don't want to ask any questions about that, but this is an example, potentially, we still don't know fully the cause of that collapse, but if in fact there was a problem with the concrete and or the rebar, it points to maybe a bigger issue of building construction over the last 50 to 60 years, at least in the US and perhaps around the world. And I'm wondering if there are lessons here, or what this might tell us about the future of materials use. And again, I'm not looking for answers about what happened in Miami, but maybe just give me your thoughts about what that tells us about composites use in infrastructure and in future buildings and structures. I'll start with you, Gareth.
Yeah, I think the first thing to say is, it's really sad, and no one wants to hear about loss of life, particularly associated with a collapse of an engineering structure, and that's sad, and my heart goes out to anyone that was affected by that. I think on the engineering side of it, it always amazes me in any environment, and particularly if we even come away from that and look at the saltwater environment. Why you would ever want to put steel close to a saltwater environment, particularly in the splash zone, when you're completely reliant on a protective coating, etc., to prevent rapid corrosion of that structure, and industries can accept that degradation and those risks associated with that technology, but as a competing technology in composites where you don't have any of those issues associated with corrosion, there's a real reluctance. So it's, I hate to use the phrase, but it's almost the better the devil you know. So there's a lot of historic information. Generally, some of those corrosive behaviors are predictable and understood, but every now and then it catches people out because the engineering environment is complex. You can't allow for everything. There are assumptions made. There are load factors applied to things. So it is a challenge, but I think real critical events like that, they can work for and against the change of new materials. On one side, it can make people really risk averse and say, well, I'm going to go back to what I know and reinforce with what I know. I don't want to add another complexity or an additional risk. But then it can also drive, I guess, the right people to be looking at and going, right, there's got to be a better way of doing this. And whether that's looking at existing infrastructure and saying, what do we need to put in to address these challenges? When they understand, what's actually happening, what are the early signs, what are the technologies we've got available, and that kind of retrofit repair for composites are really, conformable and really, from a thing that you can kind of mold with your hands that can, beat the strength of steel. It's amazing, to fit in the kind of spaces that you might need to fit for retrofit applications. So there's particularly a niche market there. In terms of, I guess, new construction techniques, we'll come back to some of the barriers to entry. We still need to address the understanding of standard certification requirements for composites in those applications, and we need access to data. And the way we're pushing it is more around the, moving into Industry 4.0, so digital technologies, so moving it to the digital design space, digital certification, and then looking, rather than saying, we haven't got 50 years of operational experience under these conditions, we can validate through digital methods what our predictable performance is, and then use things like structural health monitoring and other techniques that composites can bring in terms of their multifunctionality to actually monitor them and pair that back with a, potentially a live digital twin. So you are constantly up to date with what assumptions have we made and what's the real life data? How is that panning out compared to what we expected? But there's quite a way to go to get there. But that's kind of the vision of the future for what composites can help bring into that sector as well.
Right. Any thoughts, Joe?
So I'm not a forensic engineer, and it certainly is going to be a challenge for those folks to figure out why that building collapsed, why that tragedy occurred. But I will say one thing. It happened in Florida. And when I was talking about bridges, I mentioned that Florida is one of the most active states for using FRP and FRP rebar. And the reason they do is because they are surrounded by the ocean and they have a very corrosive environment. So the state of Florida has been a leader in the use of FRP rebar and FRP elements of bridges exactly because of corrosion resistance. And when you look at the pictures of some of the pictures I've seen of that building before it collapsed, you see corroded rebar and spalled concrete.
Okay. Well, let's get to some of the questions from our audience. We have quite a few, so let's try to get through as many as we can. Maybe we'll start with you, Joe, here. Which FRP composite applications within infrastructure do you see as having the best growth potential over the next 5 to 10 years, and what might drive that growth?
So I think that the whole resiliency push, okay, and the climate change and the sea level rise, I think you're going to see greater use of things like seawalls and FRP utility poles that are able to withstand things like hurricanes and storm surge and tornadoes and forest fires. I think that's going to be an area where you're going to see a lot of growth. I think, based on the last question, that I think you're also going to see a lot of growth of FRP rebar. I think it will be in the states where you're dealing with an ocean close by, a corrosive situation, but even in northern states where you're using de-icing chemicals to get rid of ice and snow, you're going to see more and more use of FRP rebar. And then I think that RF transparency is going to lead to opportunities related to communication.
Gareth, what opportunities do you see?
Yeah, I mean, echoing what Joe said, I think coming back to, I think it was one of the first questions you asked, I think you're still going to have the earliest applications and adopters of the technologies where there's a very compelling value proposition and business case for the use in corrosive environments, in environments where you need lightweight performance, whether that's in the construction phase or in the operational phase. I think bridges are a very good application for, even from the fact you can potentially manufacture them off site and drop them in place in a one-part lift, which causes much less disruption to traffic flow or rail activity in those applications. I think the need to get it, I think rebar is a good commodity application, where you can make heaps of rebar out of composites and see widespread use and adoption. I think the other thing is the need to move into those kind of commoditized sections, and there are companies around the world, for example, doing protruded sections, really high performance sections, whether they're in thermoset or thermoplastic, that can replace like for like steel girders, the steel sections that are kind of the foundation structures of any large building. The only barrier, as I see, is really the knowledge of the industry or the comfort with the industry to lean on composite technology to replace technologies that are so well known and well understood. It's very different because you can't go and weld things together in the same way. There are different joining techniques. So again, you've got the challenge with the current supply chain could not necessarily, accept the switch with their current skill set. So you have to address that. But I think if you address that, or if you make the joining techniques and some of the challenges that the supply chain would have, and make it as easy as possible for the supply chain to take those technologies, then I think there's much less resistance then to use commoditized sections for structural. The mainstay structural sections of buildings, and potentially there's no limit, because as you start seeing the adoption of the technology and the widespread use, it drives the cost down, and therefore you get more operational data.
Yes.
But you've got to break that seal, if you like, in terms of the adoption.
Okay. So Gareth, I'll put this next one to you. With so much emphasis on plastics currently sourced from fossil fuels, how do the greenhouse gas emissions from making FRP factor into the sustainability story?
Yeah, and I think Joe pointed to the CO2 footprint. I think there are various studies out there showing that on a like-for-like basis, where you put FRP structures in either replacement for steel or concrete, you win from a CO2 emissions perspective. Petroleum-derived products, currently, do go into the polymer systems and carbon fiber, as people understand. But there are technologies that, being in the market available in terms of more naturally derived resin systems, in terms of other fibers or even lower CO2 footprint fibers. So, you kind of got a double step there for the industry to start influencing the drivers or what they want to see from the performance of the material from either a CO2 or a cost perspective. You have to get the industry, using the material and driving the market to push those technologies in the direction they want to see. So, we're involved in that from a sustainability perspective. LCA, so life cycle cost and CO2 comes into that as well.
Okay. Joe, next question for you. This is from Marin Elliott. Is the ASCE manual and repairs available on their website? How do you determine best practice for what materials to use for repair? And maybe more broadly, do you have suggestions on how to get involved with companies or organizations that are testing potential infrastructure solutions? So maybe it's a lot of questions there, but if somebody wants to get more involved and learn more, what's the best path forward?
Right. So I'll start there, because I am a member of ICMA, which is the Institute for Advanced Composites Manufacturing Innovation. It is a Manufacturing USA institute, has over 100 industrial members, more than a dozen universities, 2 federal laboratories, and it's very much involved with testing of composites and development of new products. So IACME, www.iacme.org. With respect to the manual that I referred to is actually an AASHTO manual, AASHTO. I believe it is available on their website. I don't think it's free. And then what was the third question, Jeff? There was a third one.
Yeah, if somebody wants to get involved, let's see.
Yeah, I talked about the IACME. That's how you can get involved.
Best practice. Best practice from
best practices. Okay, so I was looking at some of the other questions as Gareth was answering, and someone asked, why do things take so long? Why is the pace so glacial? The development of codes and getting everyone to agree on standards and specifications can be a glacial process. There is one LRFD for load resistance factor design for protruded structures that ASCE and ACMA, the American Composite Manufacturers Association, have been working on for more than a decade. There was a pre-standard issued in 2010. The standard itself is supposed to come out this year. I think one of the things that needs to happen is faster approval, faster agreement on these new codes, because design engineers want to have standards and specifications. And there are already a lot out there. ACMA has a very good listing of the standards and specifications that are available on their website, including ones from the American Concrete Institute. And so I would encourage going to the ACMA website to learn about a lot of the standards and specifications that already exist.
Okay. Gareth, I'm going to throw this one to you. See what you can answer this however you like, but you mentioned end of life. So this is from Michael Connolly. End of life is always a challenge for composites. Producing a recyclable or depolymerizable resin system is typically counter to the durability benefit that composite systems typically bring. Can you share examples of resin systems today that are both durable in use but can be easily reduced to monomers for secondary use? Fairly technical question, but there's an end-of-life component there that is a challenge for sure. I just wanted to get your thoughts on that.
Gareth, if you need help with that one, I can help with that one.
Yeah, I will definitely reach across to you, Joe.
That's the chemistry. That's the chemistry.
Yeah. I've left some of those details behind in my career, so I've moved more into strategy.
So let me just jump in and say that end of life is a challenge, as was phrased in the question. You've got materials that are built to last for decades, and then you want them to come apart quickly at the end. Okay, big dichotomy. Okay, but there's a lot of work going right now on recycling of composites and end of life. Many different solutions are being pursued, and both with thermoset composites and with thermoplastic composites. And one specific thermoplastic, which is, I think, interesting, is the Elium resin from Arkema. It is a methacrylate-based polymer that forms a thermoplastic, can be used in rebar, can be used in other applications for composites, and it is recyclable. Thermoplastics are, in general, easier to recycle than thermosets. And so Elium from Arkema is one that I would highlight.
Yeah, I think just to reinforce that, I mean, some of the technologies used to break down, because like I said, you start with a product, you generally try not to degrade during operational performance, so you have to introduce some other stimulus in the environment to then break that down, and generally that will be heat in the form of direct heat or some of the technologies we're working with is superheated steam, for example, where you do start to break down the polymer matrix and then you can recover the fiber. The fiber is generally the bit you're looking for because that's the big value add. However, the resin is another value proposition in there because you don't want to end up with something else you've just got to dispose of. So breaking those down into its chemical constituents to then re-enter the value chain as a new chemical is something we're definitely looking at, because there's companies will want to do the right thing to a certain extent, But what we're trying to create is a market for recycling. So you have a customer that will want the degraded polymer or the recycled polymer in its constituent chemicals, whatever that might be, depending on the process. There's a company that we're doing some great work with, not directly involved in this project. They're in our Suswin project called Vestas, and I think you may or may not have seen some of the articles. I think the program's called CTEC, but they've developed some technology with some of the Danish universities to break down a thermoplastic polymer. Sorry, not a thermoset polymer, and being able to break it down into its constituents to then you make it into something reusable afterwards. So I would say it's not been a massive driver for the last 30, 50 years of composites, to be honest. So I think one of the challenges now is to accelerate that activity, because it's very high on the agenda for everyone using composites, and people are asking the questions who are not using composites is, am I going to end up with a sustainability challenge if I start to adopt composites? And the message is your through life sustainability is going to be markedly improved with composites, and we're working now to address the end of life. But when you're talking civil infrastructure projects, hopefully we're talking 50, 100 years plus of usable life. If you can use the composites in those correct applications. So I think that's a real benefit even from a sustainability perspective, because you don't have to you have to repeat the infrastructure manufacture and installation twice, for example, to get long life out of those assets.
And I want to echo what Joe just said about the Archimet material, the Elium. It's part of a larger family of materials, what we call reprocessable epoxies or reprocessable thermosets. That is, they're materials that cure and cross-link as a thermoset, but they can then be reprocessed and softened and reformed like a thermoplastic. So there are several companies out there that are making polymers like that right now. And if you go to the CW website and just search reprocessable epoxies or reprocessable thermosets, you'll find out more on that. All right, we're near the top of the hour, so we've got one more question, and I want to at least recognize the question. I think we're going to have to answer this question offline, but if either of you has examples to address this question, I think it would be helpful. So the basic question is, who are some of the key manufacturers in these infrastructure applications or markets? So I'm going to throw one out just to get started. There's a company in Ohio in the US called Composites Advantage, well known for making bridge and marine structures from composites, do a really good job. We've done a couple stories with them. So I'm going to start with that one. But if either of you has examples of companies that are active in this market, that might be a good resource for people. So Joe, do you have any?
Sure. So you mentioned Composite Advantage, and that is one I would mention. And they are actually part of what's called the Creative Composites Group. And so within that group, there are other companies that also provide infrastructure products. So Creative Pultrusions is part of the Creative Composites Group, and they make some of the pilings that I showed. If there's a way that you can distribute the presentations, you may have noticed, I went very fast, you may have noticed that in many of the photographs, I actually acknowledged the company that provided that part. Right. And so, and then one other one that I'll just touch upon, in terms of FRP rebar, Owens Corning. There are many smaller rebar manufacturers, but Owens Corning is a producer of FRP rebar. Okay,
thanks. Gareth, any thoughts?
Yeah, I mean, there are a huge number of companies, and I don't want to do disservice to any companies by not mentioning them, to be honest. But there's a couple of left afield from locations that you wouldn't necessarily expect or explore. So Premier Composites in Dubai, for example, some astounding structures that company have done, including apple roof made of CFRP in Cupertino. Another really interesting one that have managed to put projects and now got a manufacturing footprint in the US is a company that I knew from my time in Australia called Wagner's Composites, and they do pultruded sections, and some of the bridges actually, Joe, that you might have referenced have been some of the bridges that they've been contracted to do. And I think this is a really interesting piece, because of the lightweight nature of composites. A company in Australia can win a tender a bridge in the States on, you know, in a competitive pricing market because of the benefits that, you know, composites bring that company. They can put it into a container, they can ship it out and reduce installation costs on site. So I think the opportunity for composites and the benefits that brings, you know, companies that are willing to think outside the box on it, I think are huge. Great.
All right. Well, Gareth and Joe, we are at the top of the hour. We do have a few questions we didn't get to. So what we're going to do is I'll aggregate all the questions. I'll solicit answers from Gareth and Joe, put those all into a document and send those out to all of our attendees.
Okay. Yeah.
I'll also provide links to your presentations, assuming you are both comfortable sharing those.
Yeah, that's fine.
Absolutely.
And then I threw into the chat contact information for Joe and Gareth, their email addresses. So if you have questions that you want to direct specifically at either Gareth or Joe, you should feel free to do that. But this is great information. I appreciate both of you for coming today and for presenting. And I appreciate our attendees as well for tuning in and providing such good questions. So Gareth and Joe, thanks again for participating in the CW.
Thank you very much.
Thank you. Thank you, Jeff.
Thanks, everyone.
Thanks, Gareth.
Take care. Thanks, Joe.
All right, and that brings us to the end. Thanks, everybody, for tuning in. And join us again next month. And keep an eye on your email for the next announcement for CW Trending. And have a good day, everybody. Bye-bye.